All right, here's going to be our final example. Example number 3, this is going to be doing that radiocarbon dating idea. So carbon 14, this means that it's a carbon with a nucleus that has 14 particles, basically. Typically, you have 13 particles in carbon. Carbon has, what does it have? I should know this. I think it has 6 protons and 7 neutrons. So this one would have 8 neutrons. When it has that extra neutron, there's some physics going on in that nucleus that makes it a little less stable, makes it want to break apart. So it's a radioactive form of carbon. So carbon 14 is used to date objects in a method called radiocarbon dating. Carbon 14 has a half-life of 5,730 years. So after 5,730 years, whatever you have, if you have 10 grams of it, then you'll have 5 grams by that point. In the next 5,730 years, you'll go down to 2.5 grams. So you'll constantly just cut it in half every 5,730 years. In order to do that, that requires a decay constant of 0.00012. So I think that is a little bit bigger than that thorium decay constant that we just saw, which means that this is decaying a little bit faster. I think I have that right. So in 2016, charcoal flakes from the excavation site of an ancient human settlement in Canada were sent for radiocarbon dating. If the charcoal flakes were found to contain about 18.6% as much carbon-14 as they would have originally contained, how old are they to the nearest year? Okay, so if the charcoal flakes were found to contain 18.6% as much as they would have originally contained. Now, how much they originally would have contained, this has to do with samples are taken from like ice cores typically. So like they'll go to Antarctica and they'll drill down into the ice and take out a big long tube of ice, and they'll be able to find um, radioactive carbon that has not broken down, and that will give them an estimate for how much of that radioactive material was present at that given time. So like when it says contain 18.6% as much as they would have originally contained, you might kind of scratch your head and say like, well, how do you know how much they originally contained? There are techniques where you can take samples to sort of like create expectations for how much carbon-14 should be like in the atmosphere in any given year. So once you have that sort of metric established, you're able to compare to that number. Okay, so let's write out our equation. So we've got y equals AE negative KT. Our final amount is 18.6% as much as the initial, so 0.8186 equals 1. So whatever the original amount was, our final amount is 18% of it. So I can just say, 1 e to the negative kt. And I won't write the 1, so I'm just going to write e to the negative kt. And at this stage, we do, well, we know, what do we know? We know the k, right? We know the k, and we're searching for the t. So k was 0.00012. And we are looking for that t. So ln of 0.186. I'm going to jump forward a few steps. So when I take the ln of the right side, this part goes to the front, and then the ln of e disappears because that just equals 1. You've seen that a few times, so hopefully not too much of a problem to just jump ahead. Okay, and then at that stage, we're just dividing both sides by the coefficient in front of the t. Oops, don't want that t down there. There we go. Okay, so let's do that. Now, if you're looking at this, the expectation here is that we are going to get, let me just see if I do this, get a positive number and a negative number from that. Okay, so I get a negative number. So the negatives will cancel out in the end. So we're going to have this divided by 0.0012. Okay, so we get a value of 14,000 years. Okay, so this is a process, fairly short process, really, mathematically, that you go through to figure out the age um, of different materials in the ground. Now, radiocarbon dating, I think, based off the amount of radioactive carbon that has been in the atmosphere in the past and the rate at which it decays, there's sort of a time period for which it works. And if you go too far behind that, then the expectation is that enough of the material has broken down that you will have a hard time measuring it. So radiocarbon dating effective window is like 150,000 years, something like that. Um, See if we can get a value for that. Mm, I guess we want carbon dating, right? That's what we're talking about. Carbon dating. Time. This particular technique, using this particular isotope of carbon, will let you date things from anywhere between 500 to 50,000 years old. So anything that's older than 50,000 years, we're not using the carbon-14 method, but we're probably using a similar method using some other isotope. If I didn't give the perfect explanation on that, like, reference point idea of what they were saying back here, where they said 18% as much as it would have originally contained. Just trying to remember off the top of my head how this works, and some of these things are kind of complicated. So if you're interested in that, which I think you should be, it's a very interesting topic, just look up a YouTube video for carbon dating, and there's probably some kind of short and sweet explanation that kind of gets to the point pretty quick on what the technique is and how it works, and mathematically how it works. Okay, cool. So that is it for this lesson. Thank you for watching all these videos, and I look forward to seeing you in our next lesson.